Well, welcome back. Lesson 3 is going to be a very short lesson on simple harmonic motion, specifically looking at the simple pendulum, and we saw this on this diagram on our first page of notes, where our equilibrium position is the pendulum just hanging straight down. We're going to displace it to the right a little bit, and gravity is going to pull it back to position 0. But it's not the full amount of gravity, it's the mg sine theta portion of gravity that is our restoring force. And at first it seems like we have a problem relative to simple harmonic motion, because we know that for simple harmonic motion our force has to be of this form here. You do not have simple harmonic motion unless your force is of this form. In other words, that the restoring force is linearly related to position. In other words, if you double the position, you double the force, triple the position, triple the force, and the slope then represents a constant, and it's a constant that gives the strength parameter for that restoring force. And when we did the spring, it was F equals minus kx, so that strength parameter was the spring constant and described how strong or how weak of a spring you have. So if we need our equation to look like this, and our equation looks like this, we may think, well, we're out of luck, because the restoring force is not linearly proportional to theta. It's proportional to sine theta, which is clearly not linear. But as we saw on that first page of notes, we have the small angle approximation. In other words, if we don't pull the pendulum very far to the side, sine theta gets to be very close to theta, and let's see how good of an approximation is this. And I think we're going to see that it's a very good approximation, because even if we look at the small angle approximation, where the angle is really not that small, 57 degrees. If we take the sine of 57 degrees, we get 0.84. Well, 57 degrees is 1 radian. 1 compared to 0.84, it still is only 16% apart. So it's not horrible, but 16% is still a relatively large percent. But as we go smaller and smaller from our 57 degrees, and we get down to here, 0.25 radians, which is 14 degrees. So now not that far. Sine of 14 degrees is 0.247, and 14.3 degrees is 0.25 radians. Now look, now we're in around 1% different, very close. And that's why we said as soon as we get down to around 10% or less, you're 1% less difference in sine theta and theta, and we're in that golden region of saying simple harmonic motion will occur, because now the restoring force is such that we can replace that sine theta with a theta, and we have exactly the mathematical form of the equation that matches the block on the spring, and we have simple harmonic motion. Okay, let me clear my scribbles here, so if you want to go back and pause the screen, you can pause the screen and take your notes. But today's lesson is very short. We just have one more page of notes, which is really, let me erase all that. And one more page of notes where we're just going to, again, recap kind of what we did with the block on the spring, but now put it in terms of the parameters for the simple pendulum. So we saw from our last page, we have our restoring force. The force bringing the pendulum back to the origin is technically not the same. It's not linear. We get that mg sine theta. F equals ma, Newton's second law. So we have mass to mass, and acceleration is the calculus version of the acceleration that generates our second order differential equation of motion that describes the motion of the pendulum. So keep in mind that if that's language that you see, don't be intimidated by that. That is just Newton's second law in calculus form. We just saw that our small angle approximation is in that golden territory when you're in around 10 degrees or less. So if we're less than 10 degrees, right? So if we're 10 degrees or less, then we're in that mg sine theta becomes just mg, and now we have the same exact mathematical equation that we had with the block on the spring. Now, notice we are going to substitute in, we're going to use that theta equals arc length over radius. So this is just, we're going to put theta into radians. And what that means is the x here, let's scribble this x off and make that in s, because that s is the arc length distance that we're using here. Okay? So, when we now have our second order differential equation, the format is now perfect. And by the format being perfect, what I mean is if we go back and look at what we did with the spring, and you don't have to copy this down into this page of notes if you don't want to, because we have this on our previous page of notes, but this is what we have for the spring. We have the second order differential equation. Remember, our solution was x equals a cosine omega t, and I left the phase angle off because I don't introduce a phase angle if I don't have to. I'll start it at position positive a and let it oscillate back and forth. Our proof, if you go back and look at our notes, was a proof by substitution. So, proof by substitution. And again, that's earlier in the notes, so you don't need to recopy this. And we saw that this equality was upheld as long as omega equaled the square root of k on m, and we said experimentally that was shown to be true. And remember, omega was the frequency of oscillation, how fast or how slow the pendulum is going back and forth is based on square root of the k on m. This is radians per second, but we can very easily convert that into 2 pi f revolutions per second. So let's see what we have here. Since mathematically these two equations are the same, we're going to take the same general solution. We're going to substitute it back in and do a proof by substitution that the equation, this equation, matches our differential equation. So again, I'm not going to take the time to actually plug in all the variables, but just make a note here that this is also a proof by substitution. Hopefully your pen writes nicer than mine. Substitution. And what we get is the equality, our differential equation, is satisfied as long as the a's go, the cosine goes, as long as omega squared now equals g on L, or omega equals root g on L instead of root k on m. And again, experimentally, that is shown to be true. And the reason I have equivalent variables down here at the bottom of the page is so that when you think about how, how to relate the spring to the pendulum, you'll hopefully remember the equivalent variables. So in other words, if omega for the spring equals the square root of k on m, and omega for the pendulum equals the square root of g on L, then what we're doing is saying the k and the g and the L and the m are the equivalent variables. So if I understand that a strong spring k makes a spring oscillator go back and forth very fast, then a pendulum that's in a large g environment, like here on Earth versus on the moon, on Earth that larger g will let the pendulum go back and forth faster and faster. And how about the mass on the end of the spring? Well, a light mass, a small mass, also corresponds to the pendulum going back and forth very fast. And look what we have here, equivalent variable. The small l, the shorter the string length, the faster the pendulum will go back and forth. So this turns out to be very important for multiple choice questions where they're going to ask you how fast or how slow a pendulum or a block oscillator is going back and forth. So that's all the notes we have for today's lesson. Hopefully you see the connection between the block oscillator and the simple pendulum, and your homework questions regarding pendulums will be much, much easier for you. Thank you very much.